Hello everyone, I am Shubham Das and I am pursuing my BTech degree in ECE from Institute of Engineering and Management, Salt Lake. Today, I and my team are going to present the digital twin model for round 3 in Nginx.
Hello, I'm Shavata Handra. I'm currently pursuing my BTech degree in Electronics and Communication Engineering from Institute of Engineering and Management, Kolkata. I'm a part of the team, the Vincis, for the Nginx 2018.
Hello everyone, I am Shashwat Chatterjee and I am pursuing my BTech in Electronics and Communication Engineering from Institute of Engineering and Management, Kolkata. I am a part of the team Da Vinci for Nginx 2018.
Hello everyone, I am Shunalita Bhattacharya. I am pursuing my BTech in Electronics and Communication from Institute of Engineering and Management, Kolkata. I am a part of the team, the Vinci, and we are participating in Nginx 2018. Now we shall begin with our presentation on digital twin. Now we are going to present our digital twin. The name of our digital twin is Digital Agricultural Assistant. To begin with, first let us understand what is a digital twin. A digital twin is a digital replica of entities from the physical world. The first question that arises in our mind is what will our digital twin do? Our digital twin will be used to give consultancy and recommendation to farmers for efficient cultivation of their crops. This digital twin will display results and information about the nutrients that is deficient in the soil in the farm where the farmers will be growing their crops. This is important because the nutrient deficiency will be shown in the present climatic and soil conditions. Moving on to the next slide, let us first understand what are the problems that this digital twin will tend to solve. As we already know, in our country, due to lack of precise knowledge and about weather and soil conditions prevailing in a particular area, the farmers often end up cultivating wrong crops or crops with very less productivity. Consequently, this results in a lot of wastage and the economically, financially, as well as the personal life of the farmers are disrupted. They end up committing suicide because the yield of crop is really less. So this digital twin can be utilized so that they can maximize their crop production based on the fertilizers that the digital twin will suggest given the condition of nutrients in the soil.
Now let us take a brief overview of the proposed solution. The digital agriculture assistant that we are trying to build will bridge the gap between farmers and consultants. In this case, the digital twin will act as a fertilizer consultant in which the farmers will give input data from their soil and the model will give the output as predicted for the required fertilizer that will be needed for improving the yield of the soil. So in our case, the data we have used for training our model is a static data set, and every feature of this data set is normalized. So in case of a normalized data set, we get a much better accuracy than if we would have taken the actual datas, because in actual data the range of data that varies are maybe very high, maybe very low. For example, maybe one of the features has ranges from 1 to 10 and the other feature ranges from 1 to 1000. So in this case the accuracy uh, diminishes a lot. But if we take a normalized values, all the features have a values between 0 and 1, and this will help to improve the accuracy to a great amount. Now in our data set, the features that we have used are the soil moisture, macronutrients such as nitrogen, phosphorus, potassium, calcium, magnesium and sulfur, and we have used a micronutrient as carbon. There are other micronutrients, but carbon being the most important, we have taken it. Now, our dataset also contains a class level that is the list of all the fertilizers that we have used. And these fertilizers are mapped based on the features that are input from the user. These class labels consist of 4 classes for 4 different cases of input features. And the model that we have trained, we have coded the whole model in Python and we have trained it using TensorFlow. And we have used neural network classifier for classifying, for predicting the fertilizer output based on the features that are input from the user. In this slide, we see an overview of the system and the components that has been used to build our system. The system is smart agriculture because we are working in the field of agriculture, and the entities that we are trying to give as output, the entities that are we are trying to predict, are fertilizers. The attributes that we have used for training the model are checking the soil moisture and checking the soil nutrients that are present in the soil. The activities that our model does is predicting the fertilizer, and the event based on which the predictions are made are if the feature is within or above a given threshold, or if the features are below a given threshold, the threshold that are required for the proposed fertility. Now, the state variables that are used in our dataset are the normalized quantities of calcium, magnesium, potassium, sodium, nitrogen, lime, carbon, and phosphorus. We have also used soil moisture, and we have also used a class level that has the list of all the fertilizers that we have used. Looking into the architecture of the whole system, we have a brief explanation. In this part, the user is where the farmers are. The farmer gives the input features, and these input features are have the following categories as moisture, lime, carbon, phosphorus, and so on. Now, these inputs that are given by the farmers, they can be subdivided into macronutrients, micronutrients, soil pH, and soil water content. Now, these following subdivisions are all taken, these normalized values of the input, they are sent to the prediction model, which is actually the recommendation engine. And this recommendation engine will give the output, which is the fertilizer that is predicted. Now, the recommendation engine is very similar to a consultant, and the output will be based on the actual soil requirement. Whatever the soil is lacking, these recommendation engine will understand that and will propose the required fertilizer. In this case, the fertilizer prediction is sent back to the farmer. So the farmer can use the following fertilizers.
So in this block diagram, our recommendation engine is basically a machine learning model that we have trained and classified using a neural network. So let's first understand what is the concept behind a single neuron in the context of machine learning. As shown in the diagram, a single neuron may have different inputs. Here we have taken x1, x2 up till n inputs, and they are passed through a transfer function. And along the way, they are weighted. And these weights are unique. So we have the inputs times the weights passed through the transfer function, and based on this input, a neuron may fire or may not fire. So we are using here an threshold, which is the activation function, which may be a step function, a sigmoid function, or a rectified linear. In our case, we have used rectified linear. So this is the concept behind a single neuron. So let us understand what a neural network is. A neural network is basically a combination of interconnected neurons. And we have visualized our neural network model with Vika, which is a data mining software. So let's proceed with Vika. So this is Vika, a worldwide used software for data mining purposes. We are using this software to mathematically model our neural network. So let's begin. Here in the pre-process step, we have to select our dataset. So first of all, let's see our dataset. So this is a static dataset we have used here, and it includes 9 feature set containing macronutrients as well as micronutrients from of a soil sample such as calcium, magnesium, sulfur, etc. and the corresponding class levels according to each feature. Here we have used 4 classes for 4 different types of fertilizers, and we have used an ample amount of data to train our model, and these data are normalized data as discussed earlier for better accuracy. So let's begin. Here we have to select our dataset. Then here we can see there are 10 columns, out of which one is the class level. Now, proceeding next, we have to classify and feed this dataset to our classifier. First of all, we have to choose what classifier we are using. Here we are using neural network, in other words, multi-layer perceptron. So let's select. So now let's choose the parameters. Now to visualize the neural network, we have to set this to true and then set our hidden layers. So here we have used 3 hidden layers with 10 nodes each, but in our code we have used 500 nodes. But to visualize it properly in a figure window, we are using 10 nodes. So now let's set it, and the learning rate here we have selected 0.001. Set it to OK, and then as we are using our training set, we have to select this and then start. Here is our neural network, which is a combination of neurons, and these three are the hidden layers, whereas this part is the input layer and this is the output layer. Here we have used, as we have used 3 new hidden layers, these 3 hidden layers are having 10 nodes each, all interconnected to each other. And the result of the third layer with the clustering part, here we have to first choose our clusterer, which here we have used is a simple k-means clustering, and again we have to set the parameters. As we have 4 class levels, we have to set our number of clusters to 4 and set it to OK. And again, using the same training set, we are going to start our clustering process. Here are the clustered instances and attributes. Now, to visualize the clustering, we have to select Visualize Cluster Assignments, and here we can see the features are clustered into various uh, attributes, but such as here we have selected calcium, so the features are distributed according to the class levels. Now we are mainly focusing on the classes or the types of fertilizers, so we are going to select Y as a class and then see how our features are distributed in different classes or clusters. Till now, we have discussed about what our digital twin is and how we have modeled our neural network and visualized it in Vika. Now, let's take a look on the flow diagram of how we have implemented it on Python. First of all, we have to read the dataset, the same dataset which we had used in Vika for the classification. After that, we have to set the hyperparameters. Those are the number of nodes in each neural network, or the number of nodes, in other words, the number of nodes in each hidden layers actually, and we, we also have to set the number of classes and the batch size. After that, we have to generate the batch. Basically, we have to generate the batch because in the neural network, we cannot give input of near about 1000 or 2000 data at a one go. So we have to divide it into different batches, say about 100 features at one time. After that, we have to define our neural network model, which is uh, in which we have to take the input data, multiply it with their corresponding weights and biases, and then pass it to the transfer function, which is basically a summer. After that, we have to define our activation function, and the output of the transfer function is fed to the activation function. In our model, we have used the activation function as rectified linear unit, which is also known as ReLU, and after these processes, we have to train our neural network. In training, we have to set the number of epochs they're going to use. In our case, we have set it to 20 and found out the accuracy and other results. After that, we have to predict an output. In prediction, a user input is given where the 9 features are given to the neural network, and the neural network predicts which fertilizer or which class level which fertilizer is to be used, like fertilizer 1, 2, 3, and 4 as our class levels we have shown in the dataset earlier. After that, we are going to plot the epoch versus number of epochs, epoch loss versus the number of epochs and the cost versus the number of epochs graph to see whether our optimization and the loss is decreasing as we increase the number of epochs or not. And after that, we will print our accuracy. So let's proceed with the implementation part and see how the code is written in Python and how we have used the TensorFlow as a framework. Now let us start with our code. Here we are going to briefly explain how the code works. First of all, we are going to import our framework, that is the TensorFlow, and other necessary libraries such as NumPy, Pandas, Matplotlib, scikit-learn, etc. And then we are going to declare x in and y in, where the number of columns should be 9 as we have 9 feature sets. Then we are going to read the data set, which is our which we had used in Vika, and then we are going to drop the class column and save it in X, which is our input. That those are 9 feature sets, and the class column would be our Y, which is our output. Then we are going to set our neural network parameters. Here we have used 500 nodes in each hidden layer, and the number of classes is set to 4 as there are 4 types of fertilizers. Next, we have we have made a user-defined function to generate batch according to the user given batch size. Here we have set the batch size to 100. Next, proceeding further, we are going to define the model, our model, that is the neural network model, and set the weights and biases as random normal values for each of the layer, and the process going on in each layer, that is the addition as well as the multiplication of the weights and the biases. And we are going to declare our activation function, that is our rectified linear function, in each layer, and then we are going to return the output. After that, we have created another user-defined function, that is for training our neural network, where we are going to calculate the cost and declare our optimizer, where we have used Adam optimizer with a constant learning rate of 0.001, and we have set the number of epochs to 20. And after each epoch, we are going to calculate the epoch loss and the cost and print the accuracy as well as plot the epoch loss versus the number of epochs curve. Finally, coming to our prediction part, in prediction we have given a user input of 9 feature sets, and based on this input, our model is going to predict which fertilizer should be used or the class level. And here at the last segment, we have plotted our curve, which is the loss versus the number of epochs curve. Now, as we have completed the coding part, we have seen the defined functions for training a neural network and modeling a neural network. Now let's see how the code works. Here we can see the code is running for 20 epochs, as we have said the number of epochs to 20. Here we can see the loss is gradually decreasing as the number of epochs is increasing. That means the optimizer we have used is working well, and we in turn see that we are getting an accuracy of 97.14%, which is a pretty decent, and the prediction here is giving as fertilizer 2 for the input we have given here, that is the user input of 9 feature sets, this one, and the prediction and our model is predicting that this set of features is best suited, or the fertilizer to be used for this kind of situation is that fertilizer 2. And here we have also plotted the graph between the epoch loss and the number of epochs, and we see that the epoch loss is gradually decreasing as the number of epochs is increasing. Hence we are getting a pretty decent accuracy. And visualizing the model, as I have earlier said or mentioned, that we are going to visualize the model in TensorBoard. So we can see, so let's see it in tensor board. Yeah, in tensor board we can see that this graph is our model, that is the neural network, and each variable we are getting that the number of the inputs as well as the outputs and the attributes. Here the inputs are the normal weights we have provided, and the outputs are addition and the cost. Similarly, for other variables we can get all the necessary details about what the function or the block is doing.
So far, we have discussed briefly about our digital twin, and we have tried to mathematically model it, and we have also shown the implementation of it in Python, which was giving a pretty good accuracy as well as the desired output. Now, having reached so far, we are trying to make a cost analysis such that if we want to make this digital twin marketable, so what should be the price set to the buyers, or in short, what should be the sellable price? So we are here categorizing our selling process in two ways. In the first category, we want to sell our digital twin as an software application only. If we want to sell it as a software application only, then the cost is lesser as compared to if we want to sell it as software application along with the sensors too. If we want to sell it as a software application only, then the manufacturing cost we have calculated around rupees 300. The manufacturing cost majorly deals with the accessing the payable cloud services. Keeping the profit percentage 10%, the sellable cost is around rupees 330. If this is sold both as software application along with the sensors to be used to extract data from soil, the manufacturing cost is around rupees 4,300, which majorly includes the cost of sensors, which is shown in the next slide. Keeping profit percentage as 10%, the sellable cost is around rupees 4,470. Here is a brief description of the cost. At first, we have here taken as the first sensor, which will be used to extract the data of pH and soil moisture as well as lime indexes from the soil, which is around rupees 700. This is available in online as well as offline market too. The second sensor will be used to extract the measurements of macronutrients such as NPK, the cost of which is around rupees 3,200. And in the second category, the cost for cloud services are also included, which is around rupees 50 per hour for 8 GB if we are going to use Amazon Web Services. So now let's come to the benefit part. What benefits this digital twin is going to provide? We have estimated the sellable cost keeping profit percentage as 10%. But the economic benefits from marketing this product is a bit difficult to quantify, as this digital twin plays an important role in socio-economic scenario. We all know India is mostly an agricultural based country. The farmers often end up in lesser production due to lack of proper suggestion and guidance regarding what fertilizers they should use based on their soil condition of the cultivation field. So this digital twin providing accurate consultancy and assistance as well as suggestion to the farmers is going to benefit themselves as well as the entire nation. As we all know, in second category, as the sensors are being used, the sensors may be a bit costly. To get rid of that, each village may have one set of sensors, and various farmers may use it in different times, as digital agriculture assistant works fine invariably in any cultivation field, providing correct assistance to all farmers. In future, we want to predict the fertilizer through help of image of cultivation field and through image analysis of the terrain and training our model according to that. We are also planning to introduce reinforcement learning to make the prediction and assistance better time by time. So now we are going to represent our project plan. At first, we want to describe what progress we have made so far.
At first, we have made the data acquisition. In the absence of real data, we have used a static dataset as we showed it earlier, which consists of 9 features of the normalized quantities of macronutrients, micronutrients, soil and lime indexes. Then we have built the mathematical model using neural network as the classifier. We have shown the neural network in the data mining software Weka, as well as based on that model, we have uh, implemented our code, and we have also run our code, which was giving an accuracy of around 97%, which was pretty good. And we have also plotted the loss versus epoch curve, where it was found that the loss was decreasing with increment of each epoch. The training of the model was based on the neural network as we showed it earlier. This is two snippets from Weka, which we demonstrated earlier in our presentation. This is the model, neural network model that we obtained from the TensorBoard, which is a visualizing tool used in TensorFlow framework. We also demonstrated it earlier in our presentation. Now, after the training was completed, testing was done, as we have showed a lot of times that the accuracy was coming to be around 97%. And here is a snippet of the output. The prediction was fertilizer 2 based on the given input by the user. This is the snippet from the figure window of TensorFlow. This is the loss. This is the loss versus number of epoch curve. From here, it is pretty clear that the loss is decreasing with increment of number of epochs. So the optimizer and the model is working finely, giving a result of 97% accuracy and perfect prediction. What are the further plans to be executed? As we discussed earlier, in place of static datasets, real data are to be used from nutrient measuring sensors, and they are to be fed as input to the systems. We are planning to compact this whole digital twin and machine learning model into an Android application and packaged it in such a fashion so that it becomes convenient for farmers to use. As nutrients are measured using sensors, due to price of sensors, overall cost may be a bit high. To overcome this, we are planning to introduce prediction based on image analysis of terrain. This will reduce the cost. We are further planning to introduce reinforcement learning so that it can give more accurate and efficient prediction time by time. The fund provided by us, we will try to utilize properly, as we said earlier, that instead of static dataset, we are going to use the sensors to extract real data. The sensors are a bit costly. That's where our fund will go. The cost of the sensors have been shown in the cost analysis of in later of the presentation. For cloud connectivity, we have planned to use MS Azure, Amazon Web Services. The fund will help us to bear the overall cost. This is a brief description of the cost diagram. At first, the sensor will measure the pH and soil moisture content. Here is the multi-ion calibration meter, which will measure about calcium and magnesium quantities. As in near future, we are trying to make the prediction based on the image analysis of terrain. We will be needing a GPU. That's why we will try to utilize the fund. And in the linking process of data from the sensors with the cloud, we will be needing embedded systems. Those are included in utilizing the funds, and the use of cloud services which are payable. Those are included in utilizing the funds. So far from the beginning, we have tried to cover we have tried to give a brief overview of how our digital twin is going to work, what problems our digital twin is trying to solve. We have built a mathematical model, and we have tried to implement the mathematical model in Python. We have shown that the model was giving pretty good accuracy. Now, reaching so far, we will try to implement the digital twin from the mathematical model to the real world using the real data from the sensors, and we will try to implement our further plans, and we will try to make the prediction better. Thank you very much for your patience and valuable time.